Hello everyone, and welcome to a flight test briefing video on the Albatross UAV, simulated through using Unity game software. This briefing will go over a simulated flight dynamics assessment on the Albatross UAV, with the intention of perhaps assisting an experienced test pilot looking to prepare for their first flight of the aircraft. In this video, we will talk about some key aspects regarding the Albatross, starting with post-processing of some of the data from the simulation, involving weight and balance, thrust measurement, static control response through testing flight control configuration, and dynamic control response, including longitudinal and lateral dynamic response to control inputs, with also the testing of thrust pitch coupling. After this, we will then perform some static wind tunnel testing for analyzing flight performance of the Albatross and longitudinal trim and stability. We will then conclude with some free flight testing involving ground handling, minimum unstick speed, cruise trim, minimum and maximum trimmed level flight speed, before talking a bit about the long period or phugoid natural frequency, and finishing with a flight test circuit run around the airfield at 30 meters altitude, 20 meters per second speed. After loading the weight and balance experiment, you can see that the wheels lay on a force reaction sensor which outputs resultant force in newtons. When adjusting the position of the center of gravity, shown by the black and white orb, the force sensor readings change. A value of 0 corresponds to a CG position on the mean aerodynamic chord, or Mach. Moving this position toward the leading edge shifts the weight forward to the nose of the aircraft, and likewise moving this position towards the tail shifts the weight toward the main gear axles. From the simulation, the maximum aft limit of the CG is found to be approximately 0.13 meters from the Mach. From recording force sensor readings at the main gear and nose, overall aircraft mass and CG locations can be found using wheel reaction calculations. This shows that there is a maximum CG position difference of only 0.0126 meters or 1.26 centimeters when comparing calculated and simulated CG position values. The next demonstration is of thrust measurement. This loads a force sensor fixed some distance in front of the Albatross and measures the resulting thrust exerted at varying RPM values. The expected relationship should follow closely at y equals x plot, and as shown, this linear relationship is presented well from the simulation testing. Adjustment of flight control direction was needed so that the control of the Albatross followed a more intuitive input. This is done through changing control polarity settings on Unity, so that an up arrow input results in nose down arrow nose up, right arrow for a roll to the right, and left arrow resulting in a roll to the left. A and D keys, your left and right respectively. As seen, polarity for flap control was changed as deployment direction was initially the wrong way. Varying airspeed causes differences in control response, where higher airspeeds delivered greater control than lower airspeeds where much less damped control is exhibited. Also seen is that moving CG position forwards benefits the aircraft, reducing the time taken for pitch response. It is worth noting that testing at CG position of 30% Mach resulted in severe instability of the aircraft. Using the same experiment setup, the roll rate relationship with varying airspeeds is investigated. A following investigation is then done at constant airspeed with varying aileron input. As shown, the aircraft rolls faster with increased aileron input and fast airspeeds. Also shown is that rudder deflections take much longer, over twice the amount of time, to return to stability. Pitch recovery fares much better and improves slightly more when CG position moves forward. Thrust pitch coupling investigation allows to evaluate the pitching angle where it is least affected by the thrust from the motor, at varying y positions of CG. Here, it is found to be about 3 centimeters below the Mach leading edge. Moving to wind tunnel testing, flight performance is analyzed by producing the lift curve slope, showing maximum expected lift coefficient occurring at a 40-degree flap deflection, which produces a CL of 1.2. The drag polar with no flap deflection is also produced, showing the minimum drag configuration occurring when CD is at 0.0249 and CL is minus 0.266. The presented glide ratio then shows the best lift drag ratio of 12.79, which occurs at a CL of 0.4556. This is quite far off from the expected lift-to-drag ratio of 30 and may be due to differences exhibited in simulated flight. Longitudinal trim is achieved at zero pitching moment. As such, it is ideal to choose the elevated setting which produces the highest lift or highest CL whilst producing zero pitching moment. This is shown at plus 15 degrees elevated setting. Longitudinal stability is examined by analysing the relationship between pitch against lift at different CG positions, with the flattest plotted representing the neutral point. This is shown when CG position is at 35% Mach. Also shown here is that instability occurs when the CG position is greater than 35% Mach. Moving on to free flight demonstrations starts with ground handling. Here the aircraft can be seen taxiing with effective steering achieved at the nose, with rudder inputs. As expected, at higher speeds the radius of the turning circle also increases. As shown here, the minimum speed that produces the point of takeoff is found to be approximately 13 to 14 meters per second with the flap deployed. This increases to about 17 meters per second when the flap is stowed. When the aileron is deflected about positive 4.2 degrees, aircraft cruise speed was achieved, that is 22 meters per second when motor RPM setting was set to around 22. Minimum trim speed is achieved at roughly 17 meters per second, suggesting a theoretical stall speed of 17 meters per second as well. This is at a corresponding engine level of 12 RPM. Maximum trim speed is achieved at 50 meters per second when the engine has a max RPM of 100. From exporting trim profile data, the plot of phugoid natural frequency is produced, showing that aircraft pitch oscillates as it attempts to return to a point of equilibrium. The calculated phugoid natural frequency averages to 9.9 seconds or 0.1 Hz. And lastly, to demonstrate that the Albatross has been adequately configured, a test circle lap was done at 30 meters set altitude and at 20 meters per second speed to demonstrate stability.